Hello Year 12 Further Mathematicians. We're just going to continue with Chapter 2 from the Core Pure 1 book. 2.3 is to do with Argand diagrams. Today's lesson is called 2.3 Modulus-argument form. We discussed both of those terms last time, so you should be able to work out the modulus of any complex number, and you should be able to work out the argument of any complex number. And the main thing today is to be able to convert complex numbers into something called modulus argument form. This lesson can be compared to when you first studied equations of a straight line. You would have been introduced to the form y is equal to mx plus c. That was called the gradient intercept form. And then when you studied at A level, you were told about the gradient point form, y minus y1 equals m brackets x minus x1, and there are many other forms to express a straight line. So this is just an alternative way to write a complex number rather than x plus iy. So if we look at two Argand diagrams, or two complex planes, whichever way you want to describe them. Let's go to the form we are familiar with called x plus iy. I'm just going to call that the ordinary form for today. What that means is it goes x across and y up. Okay, and we tend to express it as a vector like that. Now the alternative for this, if I forgot about the x's and y's briefly and instead labelled in the stuff we did last time, which was the modulus, which was this length, abbreviated to that, and the argument, which would be the angle made with a positive real axis, which they tend to use the letter theta. So theta is equal to arg z. I should say arg z. Okay. Now let's pick on the one on the right and ignore the one on the left briefly. Now, if I was just given this information, one thing I could do is make a right angle triangle where the hypotenuse is the modulus of z and the argument is the angle theta. Now, just before I forget, the letter they use to represent this, to shorten it even more, is the letter r. So the letter r in complex numbers means modulus as well. So I can use the letter r for the hypotenuse and the letter theta for the angle. So on this right angle triangle, let's suppose I wanted to work out the adjacent side. If I did that, I would have cos theta equals the adjacent over hypotenuse, which is the letter r. To give me the adjacent is r times cos theta. Okay, let's suppose I worked out the opposite side. So opposite and hypotenuse is sine. So sine theta, I'll just label these on for you by the way, O and A. Opposite and hypotenuse is sine, so that would be O over R. And if you made O the subject, you'd get R times sine theta. Now remember, we were forgetting about this side briefly. But now if we remembered them, the opposite and the adjacents match up with the x's and the y's. So if you took a complex number and started off with x plus iy, like so, by the diagram and the algebra I've just done, the letter x could be replaced with the adjacent, which was r cos theta, and the letter y could be replaced with the opposite, which is r sine theta. Opposite, adjacent, y and x. Okay. Obviously, first thing that should stick out to you is the fact that there's r common to both terms, so you could factorize. So z is equal to factorize the r out, cos theta plus I sine theta. If you stare at this, in this particular formula now, there's no x's and y's, and the thing this has been described in is thetas and r's, arguments and modulus. This particular form is called the modulus argument form, and it's just another way to write the complex number. Okay, just another way to write it. Let's see how you actually come up with it though, again with an example. So let's take the complex number z, which is equal to negative root 3 plus I, and we're going to try and write it in this form, which is called the modulus argument form. So let's draw a very quick Argand diagram, real, imaginary. Which quadrant would this complex number be in? Minus root 3, 1. So let's just say that is there, so it's in the second quadrant. And I don't have to go through the algebra I did above. I can now accept this as being true, and the things which are missing in this formula are the modulus and the argument. So that's all I need to work out. So the modulus is letter R, which is short for modulus Z, and the method to do that is Pythagoras' theorem, just in case you've forgotten. 1 squared plus root 3 squared, which would be 2. And the argument is the angle made with the positive real axis. And there's many ways to do this. You could work out that little angle there and then subtract it from 180 degrees or pi radians to work out the green angle. Or you can remember the formula tan theta is equal to y over x, which in this case is 1 over negative root 3. And if you work out theta, it's inverse tan of 1 over minus root 3, which is minus 6th pi. And the thing you have to check is this angle in the correct quadrant? And the answer to that should be no. And the property for tan is there's a solution every pi radian, so they pretty much given you the wrong, or the calculator's given you the wrong one by default. It's given you the one which would be this side. So you just got to add pi to it to get 5/6 pi, and that would be the argument. And then the last line would be to write it in the form they've asked. So z would be equal to not minus root 3 plus I, but 2 brackets cos 5/6 pi plus I sine 5/6 pi. Okay? And there's a really easy way to actually check to see if you've done this right. To convert back to the original form, all you have to do is expand the brackets. So I'll just do the first bit. So 2 times that, 2 times cos of 5 pi by 6 should match up with minus root 3 if I've done this right. Yeah. Okay, so in order, it's really easy to go in the opposite direction now and work out what it would be in x plus iy. You just expand the brackets and type into your calculator. The hard bit is doing what I've just done. Well, relatively hard. Right, let's work out the other answer. So minus 1 minus I is down in this quadrant. So that's minus 1 minus 1. Call that W. And again, to work out the modulus, it is Pythagoras' theorem. So R is equal to modulus of W, which is the square root of minus 1 squared plus minus 1 squared, which is root 2. If you call the angle, this one's a little bit annoying actually. You want to work out this angle, because if you look at it, it tells you the angle they want is minus pi to plus pi, which is called a principal argument. And if I went past pi, I get a secondary argument instead, not a principal one. So I want the negative answer for this. Okay, so tan phi, I'll call it, is always equal to y over x, which in this case is minus 1 over minus 1, which is 1. And if you work out what phi is, you should need a calculator for this. A calculator will give you pi by 4. Show you shift tan minus 1 divided by minus 1, pi by 4. Which is obviously not correct. That's predicting the first quadrant, but again, it gives you the wrong one. And to get down to this one, you don't add pi, because that will give you beyond pi. You have to subtract pi to give you minus 3/4 pi. So this is going to be the trickiest bit, is finding this angle. But yeah, just keep checking your sketch effectively, and then once you've worked out both of these, you can state that W is equal to root 2 brackets cos minus 3/4 pi plus I sine minus 3/4 pi. And if you had to check your answer, you'd have to expand the brackets. I'm just going to do the second bit, the imaginary part, which is root 2 times sine of minus 3/4 pi. And looking at the question, that should be equal to minus 1. Yeah, and it is. So I pretty much know I've done it right. The questions I'd like you to complete are on page 24. And if you go for question 1 and question 3 odd parts, and then do questions 5 and 6, and that'll be it.